All right, from current slide. Any questions on anything we've done up till now? Okay, we're in chapter 1, limits and their properties, and 1.4 is continuity and one-sided limits. Okay, now half of this, the continuity part, really, really important. The one-sided limit part, it's almost as if, oh, let's make limits the course and we'll play around and do all the little things about that. Well, frankly, the purpose for doing limits is to get to do derivatives. And if you have a one-sided limit, the derivative generally doesn't exist, okay, if it's only one-sided. So to me, this is just sort of esoteric, but we'll try to go through it as quickly as possible. The objectives for this section will determine continuity, which is an important concept, at a point, and continuity on an open interval. Okay, now, anyone tell me what's an open interval? What makes an open interval? Anyone's free to join. No, that's not it.
It's from negative infinity to positive infinity.
Okay. Certainly that would be an open interval because it has no endpoint here, no endpoint there. So technically you're right, that is an open interval. But you can have much smaller intervals than that are open. What makes an open interval? Sort of just said it. There is no endpoint here and no endpoint there. It can go up to a value but not include the value. Up to a value and not include the value. That's an open interval. A closed interval includes the endpoint. Okay? So that's the difference. So we'll be talking about continuity on an open interval. We'll determine one-sided limits, which is just sort of a game we play with limits, but I don't, and continuity on a closed interval. Okay, there's the closed interval. We'll use properties of continuity, good important things there, and we'll understand and use the intermediate value theorem, which is another good important issue. So let's do continuity at a point and on an open interval. Okay? In mathematics, the term continuous has much the same meaning as it has in everyday usage. A lot of times we'll have words that when we use them technically, they mean something a little bit different from the everyday usage. Okay? I know you're in here. Is it Jordan? Okay. I have trouble reading my writing sometimes. Okay. Anyone else come in since the called roll? Okay. So continuity means about the same thing. Informally, to say that a function f is continuous at some value x equals c means there's no interruption in the graph at c. So think graphically, okay? So there's one advantage of graphs. If you're coming along here and the function is continuous at c, means when you reach c, you just keep on trucking. Okay, you may do various things there, but you don't lose the value there. Now, some of the functions we've looked at before that are, have holes in them, it'd be something up to c, and maybe at c have a different value, and then not continuous because it has a hole in the function. Okay, so this says if there's no gap, there's no interruption at c. That is, this graph is unbroken at c. There are no holes, no jumps, no gaps. Okay? So, that's what we mean to be continuous at some value x equals c. Now, this figure identifies three values of x at which the graph is not continuous. At all other points in the interval a to b, and what kind of interval is that? There's two kinds. No, that's not closed. Closed would have brackets on them. Open has parentheses. So that's an open interval. Okay? On the interval a to b, the graph of f is uninterrupted. At all other points is uninterrupted and continuous. Okay? Now, here we have value f of c not defined. Perhaps c made that 0 there, but it was a indeterminate form that you just have a hole there. That's an example of discontinuity. Only one point, one tiny little point, but it is continuous there. Now this is much more obvious. Going along here up till C, then at C it goes like this. It does have a value at C, this one didn't. Just having a value at C doesn't make it continuous. The fact that the value at C is here, and just past C is way down here without any connection. That is obviously discontinuous. This is and we'll get to these a little bit later, this is called a replaceable discontinuity, because all you have to do is define the value there, and you got it. This one's not replaceable. You cannot define any value that's going to make that continuous because it has a jump. So this is called a jump discontinuity. Replaceable discontinuity, jump discontinuity. Okay? And then this one has a value at C, but it's not continuous with the other values at C, coming close to C. So this is, I guess you could call it replaceable, okay, but it already has a value. This just has no value. That one does have a value, but, and we'll give a special value for that. Oh, they're giving it right here. Here, f of c is not defined, but the limit of f of x as x approaches c is defined from both directions. Okay? Here, the limit doesn't exist because its limit is this value from the left and this value from the right. Near the plane to meet, so you can't have it there. This one is discontinuous because the limit as x approaches c is up here, but from both directions, but that's not equal to f of c. Okay, f of c is down here. This doesn't have an f of c, so the limit does exist, and it does exist there too, but it's just not f of c. All right. Blah, blah, blah. Now, in that figure, it appears that continuity at x equals c can be destroyed by any one of the following conditions. The function is not defined at c, so continuity can't be defined. If there's no value there, it can't be. The limit of f of x doesn't exist at c. Sure can't be continuous there if there's no limit there. And the limit exists at x equals c, but it's not equal to f of c. That also keeps it from being continuous, but the limit exists here and here. This one, the function is not defined. This one, the function is defined, but it's not what the limit is. This one doesn't exist. There's jump discontinuity. If none of the three conditions is true, the function is said to be continuous at c. And here is the important definition. Okay? Continuity at a point. A function f is continuous at c when these three conditions are all met. Three that keep it from being, but these three all have to happen. First, f of c must be defined. Has to be defined. Okay? That one looks like this, not defined. Okay. Now, so f of c must be defined. The limit as x approaches c of f of x has to exist. Okay? F of c may be defined, but the limit is f of x. It's not too fair, but let me do this. If you're just looking at this, the limit of f of x as x approaches c from the left-hand side exists, and that value is defined. But it's not from the other side. So this says the limit must exist of f of x approaches c. The limit existed as it approached from the left, but it didn't from the right, f of c. If all three of those are met, the f of c is defined, that the limit for f of x defined from both directions, they exist from both directions, and if that limit is f of c, you're okay. All right. Now let's talk about continuity. This is continuity at a point on an open interval. The function is continuous on open interval a to b. Now y'all do understand the parentheses indicates, okay, the interval means everything between A and B. Everything. Every integer, fraction, decimal, real number, rational number, irrational number, everything in between A and B, but the parentheses mean not at A, not at B, or not necessarily at A or B. That's what parentheses mean. If you had brackets there, then you would have including A and including B. Now you can have mixed intervals. We're not going to run into them much, but you could have a bracket here and an open parentheses there, or you could have a parenthesis here and a bracket here, meaning that second, the first would be including A but not B, the second would be not including A but including B, okay? Being a little picky here, okay? But it's continuous on open interval when the function is continuous at every point in the interval, every real number between A and B, not necessarily at A or B. The function that is continuous on the entire real number line is continuous is everywhere continuous. So that was your example before. Technically, that's an open interval because there is no endpoint. Okay, these are not numbers that just represent it keeps on climbing, negatively or positively. So this would be continuous everywhere. Every open interval, every closed interval, every interval everywhere. Okay, so that's your definition of continuity at a point and on an open interval. Now let's consider an open interval I that contains the real number C. Okay, get that? Open interval I that contains the real number C. Could C be either one of the endpoints? Yeah. No, not if it's open. Because you see an open interval doesn't necessarily contain the endpoints. So the C has to be something between A and B. It couldn't be either one of them because those are open parentheses, open interval. Okay? If a function f is defined on I except possibly at C, it may not be defined at C, and f is not continuous, and f is not continuous at C, then f is said to have a discontinuity at C. Okay? The function f is defined on the interval that contains C, but if it's not defined, if it's not continuous at C, then it has a discontinuity. Boy, that sounds like it's almost redundant, doesn't it? Discontinuities fall into two categories, and this is what I was just talking about before. Removable or non-removable. Okay? The non-removable sometimes are talked about in other terms as well, like junk and things like that. I called it replaceable. They're removable. Okay, I was thinking about it. Okay, this is it Kiara? No. Huh? Taylor. Okay. You said Taylor. No, Taylor. Okay. Let me find you. Oh, Taylor Dion Anderson. Oh, no wonder I couldn't. This is your first time here, right? All right, good deal. Welcome. Okay, time out a little bit, folks. Let's just catch Taylor up a little bit. Number one, I teach using a package called Screencast-O-Matic, which is a dorky sounding title, but it's also a dorky little package too. It's pretty cheap, but it does the job okay. That's what this is doing. This is recording. I'm on the 14th minute of today's class. Okay, now what this also means is every previous class is already out there on YouTube video. Okay, so let's back up from that a moment. Are you familiar with Blackboard? Okay, if you go to this course in Blackboard, okay, you'll see, on the home page of it, there's a series of, at least on the instructor side, there are blue tabs here, and they go on to the next screen, a bunch of them. Near the top, probably second or third, is one that said My Syllabus or something like that. If you click on that, that's where the syllabus is. And you can see that and read it and all that kind of stuff. A little bit further down, not too much further down, there's one that says instructor contact information or something like that. Okay? On that, you'll find my locator card. That's when I'm on campus, off campus, which campus I'm home, in class, out of class, that kind of stuff. Also have my phone number, email, that kind of stuff. Then you scroll on that, or you don't, well, on my computer, it's right near the bottom of that first screen. There's one that says class handouts and more, or something sort of nebulous like that. If you click on that one, you'll find everything else I've posted there. Now that includes all the PowerPoints, either ones we've already used or we haven't used. Some we probably won't use, but all the PowerPoints from that we could possibly use in this class. Okay? Those are static. I also posted a few websites that students have either given me or I found myself that they said they found useful or I thought you might find useful. So you can take a look at those. Now, a couple of those are, I think I got those correct, are book specific, but they may not be the current edition. The website is just a little bit behind the edition. This is a fairly new edition, so they may be referring to the older edition. Others are just websites. Okay? And then the last thing I think that's on that class handouts and more, the very bottom I think it is one that says YouTube videos. You can click on that, takes you right to the class on YouTube. Now, the first day of class, that first Wednesday, I was flying back from overseas, okay? So I wasn't here. Mr. Rossi handled the class, but she didn't use Screen Systematic. So you won't get anything from that class. There wasn't much done that, I don't guess, right? But then the next class, I went over the syllabus. So you can see the syllabus up here, or you can hear me talk about the syllabus and go over it in gory detail. Now, the one I was talking about down here is probably an older version. The one up here is the most current, okay? But you'll still hear all the important stuff talked about. Then the locator card, the research paper instructions, they will be there. Now, where did I put? Oh, those are under class handouts and more. I forgot to say that. Research paper instructions are there. You can watch them, read them, or you can hear me talk about them on the YouTube video, okay? And then we talked about safety, and then we started on calculus. So that will catch you up everything we've done so far. All right. Now, where were we? Okay, I think we talked about removable and non-removable discontinuities. A discontinuity at C is called removable when F can be made continuous by appropriately defining or defining F of C. Okay, so this is if you had a hole in the graph, but the graph was continuous except for the hole, then you could just define that to be the value. Okay, or if the function had a value defined, but it left a hole up here, redefine it to be that value. And then that's called a removable discontinuity. Okay. Now, what would you say this one is? What would you say that one was? Is it a discontinuity? Yes. Is it removable? Yes. Just redefine it to be right there. Is that a discontinuity? Yes. Is it removable? No way. At C, you can define anything you want to. You won't get those back together again. Okay, hunky down. Okay? How about that? Discontinuous because there's a value down here and it goes on there. Is it removable? Yeah, by redefining this value to be up here. And if you do that, it's removable. So removable, non-removable, all discontinuities. Now, are these discontinuities? I see open circles here. No, that's an open interval. Perfectly fine for those to be not defined or whatever. Okay? Open interval. So let's discuss the continuity of each of these functions. F of x equal 1 over x. Is there a discontinuity there? Yay or nay? Yeah, we think there is. What would it be? Where is that discontinuity? X equals 0, because x cannot equal 0, can never equal 0, okay? Now, is that removable or not? Trying to picture the graph. What does this graph look like? I'm pretty familiar with in the first quadrant. It does something like this. Okay? If x is positive, y's got to be positive, right? And if x is very close to 0, that's going to infinity. If x is a very large number, that's going to 0. But it never gets to either one, right? You said that the discontinuity at 0, so you can't have any value at 0. What does it do to the left of 0? Negative numbers. If x is negative, 1 over a negative number is negative. And again, the same thing. If x is very close to 0, it's a very large negative number. Very close to very large negative number x, that's approaching 0 here. So it's going like this here and that there. You think that's removable? No way. Because it's going in completely opposite directions. Okay? So no, this is discontinuous at 0, and it's definitely not removable. What did I say about this kind of function? What kind of form is that? Undefined. Completely undefined. Most undefined functions will be discontinuous, non-removable. Okay? Now, let's take a look at that. Is that a continuous function? Does it have any place where it cannot be? X equal 1. Yeah, that can't be 1 because that makes your denominator 0. Okay? But what if you put a 1 in there? What would you get on the numerator? 0 also. And 0 over 0 is a indeterminate form. Okay? So you can't tell. It may or may not be continuous. We can't tell. It's indeterminate. It's not undefined. It's indeterminate. It may be undefined, but it's indeterminate. So, what would you do to investigate further? Plot a whole bunch of points near 1 from the left and near 1 from the right and see if they seem to be going to the same value. Okay? Or a little bit easier, what could we do? Trick we use.
Plugging in the
Second?
Plugging in the
Okay, yeah, that's what I said. You can plug in numbers, and that takes a while. What trick? Okay, now when I was taking, back when I was in college, we were on the quarter system, and we had 5 quarters of calculus. And when I was in the 5th quarter, I was so fortunate I had the same instructor, or professor, for all 5 quarters. And he was really good. He was really hard, but really good professor. He taught really, really well. We actually finished Cal 5 with about a week to spare. And he said, well, let me get you ready for differential equations. So he started giving us a few hints about differential equations because that's the next course we were going to take. And he said, you'll find the differential equations, they're really kind of bizarre and sometimes difficult to see what they're doing. He said, basically you're trying tricks. Okay? If a trick works more than a few times, call it a method. Okay? Well, this is why. I showed you a trick earlier, and the book is showing it to you too. It's worked, so use it as a method now. What? Factor. Factor that numerator. What does that give you? X plus 1 times x minus 1. The x minus 1 to go out, and then you have x plus 1. Okay? And when x approaches 1, 1 plus 1 is, you know, you'd be doing such high-level math today, did you? 1 plus 1 is 2. Okay? That would be a removable discontinuity. It's discontinuous there, but you could define a value that would work. Okay. Now here's H. Always be suspicious of piecewise defined functions. And the deal here is you want them, they may be that they come like this, you know, and then they'd be discontinuous, and that's not removable. But If they happen to be the same from either end, then they can be removed. So h of x is a piecewise defined function. Anytime x is less than or equal to 0, what is the value? X equals 1. So let's do, here's the problem. Here's the problem child where x equals 0. There's your C. What is the value of this one when x equals 0? Say again? 1. Okay, perfect. Now, this is the value when x is greater than 0. So this can never have x equals 0, but the question is, what if it was? Would it connect here, or would it not connect? So let's try 0 there, and what do you get? 1. So sure enough, that will be a continuous function. Because, and let's just show the graph on that one. They're going to show the graph on all of them, so I'll let them do it. But this is sort of a little more, whoa, I don't want that color. Okay. Okay, I want to use the darker color. Okay? So here's your function. Anywhere the x is less than 0, what kind of function is this one? Say again? Okay, yeah, but just the top part, what kind of function is that? Linear function. With what? And tell me two things about it. M and B. Slope. What's the slope? 1. What's the other one? What about 1? What is that called? Y-intercept, exactly. I should have plotted in some values here. Tick marks here. Okay, something like that. So, when x equals 0, and it is equal to 0 here, y is equal to 1, and that's your y-intercept, y is equal to 1, and it has a slope of 1, so it's doing this, okay, forever here, okay, up until it reaches 0, but it stops there, okay. What is this? What kind of function is that? That's a quadratic function that graphs as a parabola. You're absolutely right. How would you define its graph? Okay, it's going to go to the right. No, you're right. It's greater than 0. And it's only opening to the right. It's not going to be to the left because it's not counting any x less than 0, only x greater than 0. So where would it be? Okay, no. Say again? Okay. If you think about your basic, most fundamental, basic, simplest parabola ever, that would be h of x, alpha of x equal x squared. That would be down here. 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, negative 3, 9. Yeah, that's how it would look, like this. But this is a vertical translation up 1 unit. So that's going to take the vertex from being here to right up here. Hey, look at that. Even though that part is not defined at 0, it starts there and then goes up 1 and then up 3 more at 2 and blah, blah, blah. So this would be the half of the parabola there. Now, should put that in different color. What color you want it? Say again? Green? Is that what you said? I can't hear. Okay. Green. Okay. We'll do green. So this part would be like this. Okay. But that would be an open circle there because that's not defined. This part's not defined at x equals 0. This is x greater than 0. But you see that's the same value when x is equal to 0 on this side. So that's going to be continuous. Okay? The function is continuous. It doesn't have any breaks to think. It's not even a removable discontinuity. It has no discontinuity. It is continuous. So this function, believe it or not, is continuous. Those are not. Usually piecewise you think they're not, but this one happens to connect at the same point, so it is continuous. How about that function? Y is equal to sine x.
Isn't it so
Second?
I say, is it still 1 or?
Okay.
Okay.
Okay. Okay. Sin x goes from plus to minus 1 if that's what you're asking. That's the y value goes from -1 to +1. And everything in between. Nothing outside of there. The question is discussing the continuity of it. Is that a continuous function or not? Okay. Now, tangent, cotangent, secant, and cosecant, all discontinuous somewhere. Thing about sine and cosine, how do they look? They're continuous everywhere. Positive, negative, infinity, everywhere. Sine and cosine are continuous. The other 4 trig functions, not continuous at certain values. Okay? So that was continuous everywhere. From negative infinity to positive infinity. A, not continuous, and it's not a removable discontinuity. B, not continuous, but it is a removable discontinuity. C, continuous everywhere, from negative infinity to positive infinity, and D, continuous everywhere, from negative infinity to positive infinity.
On C, the first part of the piecewise version, I was confused because.
Okay, I have to say it again.
That's right. On C, for the first part of the piecewise function, I was a little confused because it's saying that x can be no greater than 0.
For
Equal
this
to
part
greater
only.
than 0. Yes.
And this part is the greater part. So
Right.
it's
So how do we
defined
do this?
everywhere. Now, if this had been x less than 0, x greater than 0, you don't have a definition of x equals 0, so it would have a hole in it there, because it's not defined there. Then that would be discontinuous, but it would still be removable. Okay? But this has a definition of every value from negative infinity to positive infinity. This covers from negative infinity up to and including 0. That would be a square bracket here, and then this would be an open parenthesis on. It covers everything. So it is continuous. And the values are the same at at the break at x, so therefore it's continuous. Let's see what they do with it. The domain of FA, this is for A part, is all non-zero real numbers. Okay? Another way of saying x can't equal 0, right? And from theorem 1.3, which of course that's all we think about, you can conclude that f is continuous at every x value in its domain. But it's not, it doesn't have, the domain is not continuous, okay? And then here's theorem 1.3, okay? Limits of polynomial and rational functions. If p is a polynomial function and c is a real number, then the limit as x approaches c of p of x is p of c. If it's a polynomial function, it's going to be continuous everywhere. Polynomial functions have 2 important characteristics. Continuous everywhere. Negative infinity to positive infinity. Polynomial functions. And they're always smooth. We haven't talked about smoothness much yet, but that's the other thing about it. But if R is a rational function, now what do we mean by rational function? It's a polynomial function divided by a polynomial function. P and Q are both polynomial functions. Okay? Well, no sweat with P. Continuous everywhere. What's sweat with Q? What can Q never do? 0. Okay? So any values of x that make Q equal 0, disallow. Okay? We've done several of these. Those are going to create discontinuities. Now, if you can go back and factor P and Q and remove that discontinuity by factoring, then it's a removable discontinuity. But if you can't factor and there's no common factor there to remove that discontinuity, then it's a non-removable. Okay? And that would be at the point C. If that is a rational function, C is a real number such that Q of C is not equal to 0, then that's going to be continuous. Okay? And the R of C will be P of C divided by Q of C, because they already say Q of C is not 0. So that's going to be continuous everywhere Q of C is not 0. Any value where Q of C is equal to 0, discontinuity. Guaranteed. Sometimes removable, sometimes not removable. The removable discontinuities of a rational function are always going to be holes in the graph. If it's not removable, they're going to be vertical asymptotes there. Never going to change. Okay? Trying to tie it back into your pre-calculus if you had it. Okay? Now, this is true if Q of C is not 0, then that's true. Okay? But still, that's not answering our question here, is it? So let's continue. At x equals 0, though, F has a non-removable discontinuity, as shown here. He surely did a terrible job of graphing this. They should have shown more of this. See, this comes like this, goes like this, and just keeps going down. Comes like this. That part's good. Reflect that across the origin, and you have this part over here. Does anyone know what that geometric shape is called? You have, okay, yeah, there's a vertical asymptote here at x equals 0. I like to say x can't equal 0 because that's what you get from that. But x should not equal 0. But what is this shape called? The shape of that curve. Anyone remember that one? Second? Not a parabola. It's sort of shaped like a leaning parabola, but it's not quite. But it almost sounds like that. Hyperbola. This is a hyperbola. It has two lobes that come close at some point and just get further and further apart. That's a hyperbola. And definitely discontinuous. Non-removable discontinuity at x equals 0. Okay? In other words, there's no way to define f of 0 as to make that continuous. As you're approaching 0 from the left-hand side, from the negative side, it's going to negative infinity. As you approach 0 coming from the right, from the positive side, it's going to positive infinity. Hey, no way to connect those two, ever. Okay? So here is the B part. The domain of G is all real numbers except x equal 1. We already said that. Now, the question is, therefore, it has a discontinuity at x equal 1. What kind of discontinuity? Well, from that theorem again, you can conclude that G is continuous at every x value in its domain. Well, x equal 1 is the only part that's excluded from the domain. Okay? And at x equal 1, the function has a removable discontinuity because it's the same from the left to right. Remember we said this came out being when you factored this, divided out the x minus 1, you just get x plus 1. It's that same function we had before. It's the straight line with the y-intercept of 1 and slope of 1. Okay? But not defined at x equals 1. You can't do it because the original function undefined there, so you have to put a hole in there. But obviously that's removable because you can assign a value there, x equals 2. What would be if x were equal to 1 when you divided this out? 1 plus 1 over 2. Yeah, that has a removable discontinuity. Make sense? Blah, blah, blah. Okay, by defining g of 1 as 2, then the redefined function is continuous for all real numbers. Okay? Now, 1c. That was the one we drew, and that's pretty much how it looked, right? Had that same x plus 1 on the left part, and then picked up and went a parabola from the same point on the right-hand side, and since they did share that same value at 0, the defined value for here, and if you had included that here, they were the same value, so sure enough, that is continuous. Okay? The limit of h of x, as you come from the left-hand side, is 1, because that's the value of it there. From the right-hand side, the limit is still 1. Okay, so that's continuous on the entire real number line, negative infinity to positive infinity. Okay? D. The domain of y is all real numbers. And here's basically what it said. Let C be a real number in the domain of the given trigonometric functions. Okay, I sort of hate when they do this. They cover something here by saying that let C be a real number in the domain of the trigonometric function. Then the limit is x approaches C of sine x is sine C. Big surprise, the limit is x approaches C of cosine x is cosine C. Yeah, okay, I'll buy that. Here's the thing. Let C be a real number in the domain. So the big question is not what the limit is, it's what the domain is. And what's the domain of sine x? All real numbers. What's the domain of cosine x? All real numbers. What's the domain of tangent x? Ooh. Well, what is tangent x? Sine over cosine. So therefore, the domain of tangent x is all places where cosine x is not equal to 0. And where is cosine x equals 0? Second? You should know you're in my trig class, okay? And I think you probably was too, so I'm expecting answers. Okay. Where is cosine x equals 0? I hear it mumbling, but I can't make it out. Second? A little louder. Okay. All your half pies. Cosine 0 starts at 1, at 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, yeah. Every half pi. And negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative, okay. All your half pies. So, yeah, this is true everywhere in the domain, except the domain does not include any of the half pies. And if the half pies is discontinuous and non-removable. So, because the tangent function looks like this, and then picks up here and goes like this, picks up here and goes like this. At those half pies, coming from different infinities. No way at all. Okay? How about cotangent function? What would be its domain? That's where sine tan equals 0. And where is sine equal to 0? At 0 and every whole pi, yeah. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. At 0, all those, so you have to exclude that. Let's see, do I remember who this kid is? Is he in my class? All right, here is, I've got to find you, Tyler. Okay, good deal. Welcome back. Okay. Now, so this is certainly true that as x approaches some value, the trig functions are the trig function at that value as long as it's in the domain of the trig function. So tangent domain is all real numbers except the half pies. Cotangent is all real numbers except the whole pies. How about secant? We have another one in the class that should know the answer to that. So I know who his trig acceptor was. What about secant? Tell me what secant function is defined as. It's a reciprocal function. What's this reciprocal of? Cosine. Okay? So everywhere cosine is equal to 0, not in the domain. Everywhere else, this is the value. Okay? So what do we exclude here? Half pies again. Okay? So basically its domain is identical to the domain of tangent. The functions aren't the same, but the domains are the same. How about cosecant? 1 over sine, so therefore anywhere sine is 0, you have to exclude that from the domain. And where is sine 0? The whole pies, exactly. Okay, good deal. So therefore, since we had sine function defined everywhere on this domain is all real numbers, so therefore this is true everywhere. This pattern continues and continues and continues and continues in the positive and negative direction. That's what's beautiful about sines and cosines. It's smooth, continuous functions everywhere. So it's continuous on the entire real number line. All right, one-sided limits and continuity on a closed interval. Two different subjects here, but covered in the same subsection. To understand continuity on a closed interval, you first need to look at the different types of limit called the one-sided limit. Okay? So, for instance, the limit from the right, or the right-hand limit, means that as x approaches c from greater values than c, then we say, and here's how we express that, the limit as x approaches c from the right-hand side, from the positive side of c, okay, of f of x is equal to L, we put c with a superscript plus, okay? If you're going from the other side, you write c from the superscript negative, from the negative side of c. Even though it still may be a positive number, but it's from the lesser value than c. So this is this one. As x approaches c from the right-hand side, right here from the positive side, then your f of x is approaching this value L. Yeah, we can see that. That's a nice, smooth, continuous function. So yeah, that's going to be true. Okay? Now, similarly, the limit from the left, or the left-hand limit, means that as x approaches c from values less than c, they don't have to be negative, but just less than c, on the negative side of c, this limit is denoted as the limit as x approaches c from the minus side, so you have a superscripted minus sign of f of x is equal to L. And sure enough, this is. As x is approaching c here, your f of x is approaching that same L. So, these two limits from the right and the left have the same value. Limit approaches c from the left, that exists as well. Okay. So one-sided limits are useful in taking limits of functions involving radicals. Okay. What's special about radicals? Besides being so much fun to do, okay? Say again? I can't hear it. You can convert them, is that what you said? Okay. You can, but you have to be careful when you do so. Okay? The other thing about them, if this n, the index of that radical, now, most times just see a radical like this, how do you read that? This expression right here. Square root of x. If you have a number in there, tell me what number could be in there. 3, 4, 5. Only positive integers greater than 2. Okay? Any other, that would be the third root of x, the fourth root of x, the fifth root of x, the 15th root of x, the 434th root of x, whatever. Okay. Those are all valid numbers, okay? Or expressions. Okay? What's special if n is even? Okay? Now n can never be negative. If n is even, including the 2, which everywhere else in mathematics, like for coefficients, if you don't see a coefficient, you understand it to be 1. If you don't see an exponent, you understand it to be 1. If you have a radical and you don't see an index, you understand it to be 2. That's the only thing in the world that I can think of in math. If you don't see it, you don't assume it's 1, you assume it's 2. So that would be a square root, the second root. If that is an even integer, which they all have to be integers, positive integers, if that's even, then what can x not be? Negative. Okay? You can't take the square root of a negative number. You can't take the fourth root of a negative number. You can't take the sixth root of a negative number. Can you take the third root of a negative number? Sure. If n is odd, no sweat. But can you take the 434th root of x if x is negative? No, because that's an even index. Okay? So, if n is an even integer, and you're doing a radical here, you can't have any x's on this side. So then you only have a one-sided limit. Okay? And as that x is approaching 0, which is as small as you can get, because anything less than that becomes negative, you can't go there, then the limit as x approaches 0 from the right-hand side of the nth root of x is always going to be 0. Okay? Now, you can't do the limit as x approaches 0 from the left-hand side, from the negative side. If this is an even integer, they don't exist. They don't ever exist. So this is what you call a partially closed interval. Close on the left, 0. X can be 0. Can't be anything less. It can be anything greater. So that's from closed interval 0 to positive infinity. You can do that. So this is one place that you do need to think about one-sided limit. You can't approach 0 from the left-hand side if that's an even radical. Okay? Can anyone think of another function that would sort of be in the same boat or similar boat? You're building an old backwoods-looking cabin, and you're using log. Okay, log. I thought you were going to say log. Okay, log functions also fit into this. Because what's true about log functions? Any log, or log log or ln log. You can't take the log of a negative number, just like you can't take the square root. So they're just like it, or is there a difference? There is a difference. How?
It's a different function.
It's a different function for sure. But the domains are also different. Because you can take the square root of 0, you can't take the log of 0. Any log of 0, ever. Okay? So that's the difference I was trying to pick at. Can't take a log or a square root of a negative number, but you can take the square root of 0, you can't take the log of 0. But you can take the log or the square root of any positive number. So the same thing would hold for that, except this would not be true for logs. As x approaches 0 from the right-hand side, the limit doesn't exist. Does exist for square roots, doesn't exist for logs. But it exists everywhere greater than 0. Okay? So in other words, that would be an interval with a parenthesis. This is an interval with a bracket. Okay? So here's example 2 on page 76. Find the limit of f of x equal square root of 4 minus x squared as x approaches negative 2 from the right. Okay? How would you try to do that? Ooh, I'm still green. Let me get out of green. Okay, we're looking for the limit as x approaches negative 2 from the positive side, from the right-hand side, of the square root of 4 minus x squared. What would you attempt to do that? Plug it in. Yeah, let's try it. Plug into negative 2. Well, what do you get when you square a negative 2? Positive 4. 4 minus 4 is 0. Square root of 0 is 0. Okay? 0 squared is 0. So sure enough, that's fine. Can you approach negative 2 from the left-hand side? No, you can't. Because anything less than negative 2, when you square that, it's going to be something greater than 4. And you have 4 minus 4 is a negative number. You can't ever take the square root of a negative number. Okay? So that was not what they asked, but I threw that in at no extra charge. Okay. So, any questions on that? Let's see what they do with it. They may draw a graph or something. Yes, they do. Okay. As shown in this figure, the limit as x approaches negative 2 from the right-hand side is indeed 0. Now, how did they get this figure? this goes back to something you were saying. What's another name for f of x? Y. Good, y'all got that one. Is equal to the square root of 4 minus x squared. Now, what did you say you could do to this? Did you say clear the radical? You said something about the radical.
Oh, that's convert it.
Convert it. And what do you mean by that? What would you do to convert this? Second? Okay, you went, so I couldn't understand. Square both sides. That will undo a square root, right? So what this gives you? Y squared is equal to 4 minus x squared, right? And then you can add x squared to both sides. And that gives you x squared plus y squared is equal to 4. Okay? And what's that a graph of? Don't recognize that? It's a circle. Radius 2. Anytime you have squares here, same coefficients for the squares, the plus sign in between, equal to some positive number. That can't be a negative number there, can it? So you can't do a plus and a plus, add them together. Anything squared is positive, anything squared is positive, or at least non-negative. You can't add two non-negative numbers together to get something that's negative. This doesn't happen. Okay? So that would be a circle. Okay? The problem with that would not be a function. Okay? Because then the vertical line test fails. Okay? So what we have is the positive square root of this. So it's the upper half of that circle. You could have written that as a minus y, f of x equal minus that. That would have been the lower semicircle, but not the upper. Okay? And you see from this, or even the whole circle, the function is only defined from negative 2 to positive 2, inclusive, okay, including the endpoint, and nothing outside. Okay, so sure enough, that's what you get. So they drew the graph. That's one way to do it. I just plug it in, see what happens. Okay, and if you're approaching from the right, sure enough, you're going to get to it. All right. Any question on that? All right. They're skipping. No, I'm sorry, they're not there yet. Okay, one-sided limits can be used to investigate behavior of step functions. Y'all remember what those are? Functions that are a certain value, then another certain value, then another certain value, like that. Are those continuous functions? Hey, when you go up a step, it's here, approach from the left, here, approach from the right. Two different values. If it were curved like that, yeah, no problem there. But these are definite steps, horizontal in between. No way that's going to be continuous. Okay? So one-sided limits can be used to investigate the behavior of those step functions. A common type of step function is called the greatest integer function. And math books just absolutely love this function, though it doesn't really, in my mind, have that many practical applications. Okay? There probably are some, but it's not that many, where this is defined. Now, this looks like a bracket with an absolute value in between. I don't know. It's just that's the greatest integer function. Okay? And what that means, the greatest integer in this, the answer to this is always going to be an integer. Usually n represents integer. So the greatest integer in x will be the greatest integer in such that n is always less than or equal to x. So what is the greatest integer in 2.5? So that integer is less than or equal to 2.5. It has to be an integer. Not that hard. Okay, what? 2. Exactly. Okay? And in fact, for positive, decimal, or mixed numbers, just throw away the decimal. That's it. Okay? And when you go on the negative side, you have to sort of change your thinking some. And in fact, we're going to go negative. What is the greatest integer in negative 2.5? Say again? Negative what? 3. You're absolutely right. Here's the other way to think of this. Think of that number on the number line. Okay? Plot it. Okay? 2.5, here's 0, 1, 2, 3. 2.5 is right there. Look to the left to the nearest integer, that's a 2. But, here's the 0, negative 1, negative 2, negative 3, negative 2.5 is there. Look to the left, the greatest integer is negative 3. So that's another way to look at it.
Why do you always look to the left?
Because its greatest integer, n, is less than or equal to x. That means it's on the left-hand side. And we like lefties, don't we? Answer yes. Okay, good. Say again? Well, yeah. That's the definition of the greatest integer function. The greatest integer in n such that n, the greatest integer in such that n is less than or equal to x. That's the greatest integer in x. And it sort of makes sense. Greatest integer in 2.5 is 2. Over here you have to think what's to the left of this. That's negative 3. The greatest integer less than or equal to negative 2.5 is negative 3. All right, good deal. Now, are they going to do example 3? I don't think so. I guess just for completeness sake, we ought to do example 3. Find the limit of the greatest integer function, okay, as x approaches 0 from the left-hand side and from the right-hand side. So what we're looking for is the limit of the greatest integer in x as x approaches 0 from the left-hand side, that's the negative side, and the limit as x approaches 0 from the right-hand side, the positive side of absolute value x. Okay? Now, they graph it first, and let's just use some of the ones we just did, like here's 1, 2, 3, 4, negative 1, 2, 3, 4, 5, positive 1, 2, 3, 4, and negative 1, 2, blah, blah, blah. Okay? Now, not good. Okay. Let's change this to a negative 1.5. What would be the answer to that? Say again? No, the greatest integer less than or equal to negative 1.5. Negative 1.5. What did you say? Negative 2. Okay. I had to drop back because I didn't have a negative 3 on my scale. Okay, here's negative 1.5 here. Okay, and the y value then would be negative 2. Okay, 2.5 is over here. Its y value is going to be positive 2. Okay, if I could write that in the right place. Okay, now let's start with 0. The greatest integer in 0 is less than or equal to 0 would be 0. Okay, and that would be true for 0.1, 0.2, 0.3, 0.4, 0.5, 0.7, 0.9, 0.95, 0.999, 0.9999999, you know. So basically it would be every value here but not 1, because the greatest integer in 1 is? Greatest integer in 1 is 1. Okay. And then that would also be the greatest integer in anything greater than 1, 1.1, 1.2, 1.3, 1.9, 1.999, 1.99999, up until 2, but it's not 2 because at 2 it's 2. Okay? And then there's your 2.5, and an open circle here, closed circle here, if I could get it to right, okay? And then like this, open circle there, closed circle here, all the way over, open circle, and so on and so on. That's why we call it a step function. Let's go negative on it. The greatest integer in -1 would be -1. Greatest integer in something just slightly more like -0.5 or -0.9 or anything else, that's going to be here up to 0, but at 0 it jumps up here, right? And then same down here, this would be a -2 up to the endpoint at -1 it jumps up. So this is your step function. And you see that the values we identified before are indeed on that. So the question is, what's the limit of this function as x approaches 0 from the left-hand side? So x is approaching 0 from the left. What is the limit of that? -1, right? As approaches 0 from the right-hand side, 0. Okay? In fact, it's equal to 0. So this is -1, and this is 0. Do you think you'll ever get those to meet?
No.
Say again?
No.
Well, no, not going to happen. Okay? So this is a non-renewable discontinuity when anytime you're approaching from the left and right of any integral value. Anywhere else, if you're approaching 2.5, 2.5 from the left is 2. 2.5 from the right is 2. So yeah, that's fine, but not at the integral value, because that's where you have your jump discontinuity. Okay? So that was example 3. All right. Now, top of page 77. When the limit from the left is not equal to the limit from the right, the two-sided limit does not exist, ever. So that step function doesn't exist at any integral value, does exist at any non-integral value. The next theorem makes this more explicit, the existence of the limit. Okay? Let f be a function, c and l are both any real numbers, then the limit of f of x as x approaches c is that value L if and only if, in fact, it's only certain that the limit as x approaches c from the left of f of x equal to L, and the limit as x approaches c from the right of f of x equal to L. Both of those must be true for the limit to exist. Period. We've already been doing that, we just didn't explicitly say this. Notice someone just had to leave. It is an hour and 25 minutes into the class. That's a bit over halfway. You want to take a quick break? I call it a bladder break, but it can be any other break, caffeine break, any kind of break. Want to take one quickly? Okay, I'm going to pause this for now. All right, any questions so far? All right, that was theorem 1.10, top of page 77. Okay, that's followed by the concept of a one-sided limit allows you to extend the definition of continuity to closed intervals. Not just open intervals, but closed intervals. Basically, a function is continuous on a closed interval when it is continuous in the interior of the interval, yeah, and exhibits one-sided continuity at the endpoints. Okay, in other words, the endpoint, if it's continuous there, it has a value there. Okay, that is stated formally in this next definition, which is pretty straightforward, I think. A function f is continuous on a closed interval, a to b. Notice you have brackets here now, meaning you're including the value a in that interval. Before, when you had parentheses, it includes everything between a and b, but not necessarily a or b. So this is continuous on a closed interval. When f is continuous on the open interval, sure, it's got to be everything in between, and the limit as x approaches a from the right-hand side is f of a, and the limit of f of x when x approaches b from the left-hand side is f of b, then it's continuous on the closed interval. the function f is continuous from the right at A and from the left at B. That's what that means. So then we express that by putting solid dots there. Before, if it was on an open interval, those are open circles, not solid dots. So this is continuous on a closed interval. What's the big deal? Okay. Most of the time when we're dealing with stuff, we're only interested in what's inside the interval. Most of the time. There may be some places where this will make a big, big difference. Okay. So let's do this one. Can discuss the continuity of f of x equal the square root of 1 minus x squared. Isn't quite the same problem we had before, but one very similar. Where is that function f continuous? Well, I'd suggest a good place to start is where it's defined. Where is that function defined? All right, maybe that's not a good place to start. No. What kind of function is that? The basic function of that one? The square root function. And what is true about square root functions? What's inside the radical cannot be negative, right? So let's express that mathematically. That was big long words there. What's inside the radical here is 1 minus x squared. And how can we say cannot be negative? Written in math speak. Symbols. Is what?
Can't be greater than 1.
Okay. Okay, I think I know what you're saying. Okay, let's express it this way. This has to be greater than or equal to 0. Isn't that right? What's inside the radical has to be non-negatives, meaning greater than or equal to 0. That's math speak. Now, what does that mean? Okay. One thing you could do here is add x squared to both sides of the radical, couldn't you? That's both sides of the inequality. That's legal in most states, right? Add the same thing to both sides, you're still, inequality holds. So now we have 1 is greater than or equal to x squared. Okay? Now, I think this is the same thing you were saying. What did you say?
So like x can't be greater than 1.
X can't be greater than 1, you're absolutely right. Is that the only thing?
It can't be greater than or it can't be less than 1.
Exactly. You just nailed it on both ends. Okay? If you can see this right off the top, you can just write it down. Negative 1 is less than or equal to x is less than or equal to 1. Okay? X has to be less than or equal to 1, otherwise, that's a negative number in there. But x also has to be greater than or equal to negative 1. It can't be less than negative 1, or that is a negative number. So sure enough, we have that. What does that define? A closed interval. You see, when you have a strict inequality there, that's an open interval. When you have the equal sign there, that makes it a closed interval. So in other words, the domain of this function is from -1 to 1. Closed interval. Okay? Now, is it continuous there? That's the issue. I'll contend it's continuous everywhere in between, but is it continuous at the endpoints? Yes, because when you plug in +1 or -1, you get a 0, and that's what it's going to. Now, the other way to do this, and that's what I thought maybe someone would do, but they didn't, is go back and call that f of x. What can we call that? Y is equal to the square root of 1 minus x squared. Square both sides. Y squared is equal to 1 minus x squared. And add x squared to both sides. And that gave you x squared plus y squared is equal to 1. And what's that a description of?
Circle.
A circle of radius 1. So you can draw that circle, centered at the origin, by the way. I didn't say that before. Radius 1, so that goes from +1, -1 to +1, including the endpoints. Okay? So sure enough, that gives you the same thing. All right. Let's see. Let me erase my scribble here. Let's see how they approach it. Same way I did. They started off with saying, what's the domain of this? And just like you saw, something between -1 and 1, including the endpoints. Okay? At all the points on the interval, the continuity follows from theorem 1.4 and 1.5. Yeah, that's what we were. Oh, here's 1.4. Okay? It's funny. They give you the examples and then give you the theorems that make it true. Usually they give you the theorem and then show you the example. So the limit of a function involving a radical, let n be any positive integer, making it usually the index. The limit below, down here, is valid for all c when n is odd. Okay? We haven't done this with odds before, but we're going to do it now. And is valid for c greater than 0 when n is even. Okay? So basically, when n is even, c has to be greater than 0. I don't really like that because it should be greater than or equal to 0. But I'm not going to pick on that. But if n is odd, then it's good for all c. You can take the cube root of a negative number. You can take the 7th root of a negative number. No sweat. Okay? Maybe a little sweat, but you can do it. Okay, so the limit as x approaches c of this is going to be that. As long as c is positive for even ends, any value for odd end. Okay, that's limit for 1.4. So that's where does that come into play here? This would be as x for our problem up there. This would be as x is approaching +1 or -1, or c equal +1 or -1. Okay. And here's theorem 1.5, the limit of a composite function, which is exactly what that function is. You have a function inside another function. That's a composite function. Remember that? Alpha g of x. Your f of x would be the square root function. The g of x would be 1 minus x squared. Okay, if f and g are functions such that the limit of g of x as x approaches c is L, and the limit of f of x as x approaches L is f of L, okay, then the limit of f of g of x as x approaches c will be f of the limit. See, what you can do here, you can interchange the limit of the function and do f of the limit of g of x as x approaches c. Well, you know that is L, so that's f of L. It almost feels like you're doing circular reasoning here. You're not, but it seems awfully close to it. Yeah, well, you do this, make it that, and then you can do this and it's that. Okay, yeah. Okay. So, going back to example 4, or going down to example 4, or actually it's, they've gotten me confused now. Oh, I know what they did. They went back to earlier theorems and just stated them again. I'm sorry. They had already done those theorems before. So I misspoke. So, because the limit as x approaches -1 from the right-hand side, the upper side, that limit does exist, and that would be 0. Because you plug in a -1, you get a 0. Can you approach, is there a limit as x approaches -1 from the lower side? Can you put a minus right here? Does that make sense? No, it doesn't. Because if x was less than the -1, on the left-hand side of that, this thing would not be defined, because that would be the square root of the negative number. So you can't use the other, okay? But from the right-hand side, that sure enough is 0, and that's equal to f of -1, if you plug that in. You can also here approach 0 from the lower side, the left-hand side, and you sure enough get 0 again. You cannot approach x 1 from the right-hand side, because then you'd be coming to a greater value than 1, and if you put any value greater than 1 there, this becomes negative. So you can't do the other. So it's continuous from the, I think they said these backwards, didn't they? No, right. It's continuous from the right going to -1 and continuous from the left going to positive. Okay. You can conclude that f is continuous on the closed interval because the value is that at -1 and positive. And that's your graph. It's half the upper half of the semicircle, including the endpoints. Okay. There you go. Any questions on that? Okay. There is an example 5 that's not covered in the slide set here, so let's do it here. Example 5. This is not my law, okay? It is Charles's law, but it's not mine. This is a guy whose last name is Charles. On the Kelvin scale, absolute 0 is the temperature 0K. Now, I don't know if you've hit this in physics before, but if you haven't, let me emphasize this. When you're talking, what scale do we usually think in? Fahrenheit. When you refer to a temperature in Fahrenheit, what do you always put? A degree symbol, because it's so many degrees Fahrenheit. Now, what we usually think of as a metric type of temperature would be Celsius. It really may be metric, but it's not SI. And when you talk about Celsius temperature, you put degrees Celsius. Now, Kelvin is related to Celsius, not related to Fahrenheit. Kelvin is absolute 0. Okay? You see a problem with either Fahrenheit or Celsius. There's a 0 down here, and you can have negative numbers. Right? 0 Fahrenheit is really cold, but you can have negative. Go to, what's that place in upper Minnesota in the wintertime? It gets really cold up there, right? I can't think of that. International Falls, maybe, or somewhere in Montana. Quite frequently you get less than 0. Okay? So you can't have a negative temperature. Okay? Celsius, same way. Anything less than freezing is negative. Your refrigerator is going to be negative. So yeah?
Well, I was saying like absolute 0.
The absolute 0 means you can't get any colder than that. You can't go negative from that. That's as cold as you can go. And that's what 0K is. Now notice with Kelvin, never, ever use a degree symbol. It's just 0K. 17K. How about negative 3K? Can't happen. Okay, you can't go negative on the Kelvin scale. Now why is that important? Because some formulas in physics, you take the square roots of your temperature. And if that temperature is negative, you can't do it. So that's why Lord Kelvin, his name was William Thomson, came up with a absolute scale that you can never go negative on. Now you can take square roots of things. So that's what Charles's law is doing here. On the Kelvin scale, absolute 0 is 0K, and you can't get any colder than that. Ever. Anywhere in the universe. Ever. Okay? Although temperatures very close to K have been produced in laboratories, absolute 0 has never been attained. And by the way, that is the third law of thermodynamics. If you have done physics yet, usually you don't get into that too much in it, but that is the third law of thermodynamics. Absolute 0 may be approached, but never attained. And there's several different ways to interpret that, but that's what third law is, third law of thermodynamics. In fact, evidence suggests that absolute 0 cannot be obtained. How do scientists determine that 0K is the lower limit of all temperatures of any matter anywhere? Okay? And that's a sort of a rhetorical question here, I think. What is the absolute 0 on the Celsius scale? okay, on the Celsius scale. Boy, okay. This is a strange way to ask that question. Okay. The determination of absolute zero stems from the work of the French physicist Jacques Charles. Okay, his last name was Charles. I just gave you Charles's law. Charles discovered that the volume of gas, and okay, now it's making sense. Why did I do it? Charles discovered that the volume of a gas at constant pressure increases linearly with the temperature of the gas. And you probably recognize that, do you? Okay. The volume of the gas increases linearly at constant pressure now with the temperature of the gas. Okay. Here's a dumb example of this. When I was in graduate school in Nebraska, there was a lady at our church that her husband had, they divorced, and we moved to a city a long way away, and she had a young boy. She thought he needed some male kind of, you might say, role model type thing. And I thought, I'm single, I don't know anything about being a dad. Nope, not me. Until he came, he was a real good athlete, even in early high school. He came out for the church softball team and really was a great third baseman. I was playing catcher because that was the least skilled position in slow pitch that you had. So I wasn't good at anything. But he was a little shy being around all these guys, older guys, and so I sort of befriended him and did things. And we got to do it. I said, well, maybe I can do it. So I started going over and doing things on weekends and stuff. And one time it was in the fall in Nebraska, it could get quite cold. He wanted to shoot some hoops on a Sunday afternoon or something like that. But he had left the ball out overnight. And it was pretty cold. He said, oh, I must have punctured the ball because it's flat, okay? The volume has decreased. I said, why don't you put it inside for a while and we'll pump it up later. Well, he was going to happen. So he put it in the house where the house was nice and warm, and maybe 30, 40 minutes. So I said, you want to get the basketball? He said, well, we need to pump it up. I said, it's going to get back up. But there it was. Tight again. Okay, why? Because the volume varies with the temperature. Increased temperature, increase the volume. So he didn't need to blow it up. That's my introduction for him of Charles's law. Okay, so we didn't talk about that too much. But anyway, so as you increase temperature, you increase the volume at constant pressure. Remember that. Well, let's turn that thing around and send it this way. As you decrease temperature, it's going to decrease the volume at constant pressure, right? So you have volume here at a given temperature. So we're going to have a temperature on this scale, our volumes on this scale. So you decrease temperature, decrease temperature, decrease temperature. And this is a linear function. Linear function. And it seems you're going. Now for one gas, the slope might be this. For another gas, it might be that. For another one, it might be that. But they all have this. But guess what? You plot them all on the same scale, they all tend to be going to the same point. Now they never get there. Because if you cool a gas really, really cold, what does it do? Well, before it freezes, it becomes a liquid. So the volume decreases really quickly. So you cool these gases, and then at some point, they're going toward the same point, but they never get there because at some point they condense and become a liquid. The volume almost goes to zero. And if you continue cooling, then it's going to freeze. Okay? But when it ceases being a gas, you lose any more data on your points. But the slopes all were heading toward the same point, and that's what they decided to call absolute zero. That's where, now think of what your Y scale was here. It's your volume. So the volume disappears. Do you think it'll ever disappear? No, but you got molecules in there, so it's not going to happen. So there's another reason you can't ever get to that. Okay? You can approach it, but you never get there. Okay. So that's long, drawn out Charles's law. Okay, Charles discovered the volume of gas, blah, blah, blah. Okay. Here are some of the things he worked on here. Let's see if it, oh no, this isn't on this graph. Yuck, I hate having to draw this. So here's what it looks like here. And it gives you a table here. And now let me put that at the bottom. Okay. Okay. And it gives you a table with the values. I'm not going to plot them, but let's just say they're going along like this. Now, they never get there, but if you were to draw a linear approximation there, this is where they would intersect. And if you use the values they gave you and keep extrapolating that way, you find, and my graph doesn't look nearly like theirs, you get that's going to be something between negative 200, and this is degrees Celsius, by the way, degrees Celsius, and negative 300. Don't want that to happen. Okay. Negative 300 degrees Celsius. Okay. Now, those are awfully, awfully cold temperatures. Play around with it a bit, wiggle around it. Negative 273.15 is where that comes up being. Negative 273.15 degrees Celsius. That's what we call 0K. Never use a degree symbol with K. You can't get any colder than that. Your gas aren't even going to get there. It's going to become a liquid well before that. But it will never reach that, but you can approach it. And they have approached it really, really, really closely. What they usually use is they try to get to solid hydrogen. Okay? That is awfully cold, but it doesn't quite get to negative 273.15. Okay. It looks like they showed exactly the same table, and I don't really, oh, no. No, they're using Fahrenheit temperatures now, okay? And they just happen to use the same temperature, but on the different scales, and you get to the same point. Okay. That was example 5 in a shortened version, okay? So let's move on to properties of continuity. Now, there's a guy featured on page 79, Augustin Louis Cauchy. Okay? Have we mentioned him before?
Yes.
We have. Okay, good. I thought we had, but I'm teaching 4 different math classes, and I couldn't remember which class I mentioned him before, because he also does things in other subjects as well. But the concept of continuous function was first introduced by this guy, Augustin Louis Cauchy, French. So I don't know if I'm pronouncing it right. The definition gives in his text, the course of analysis, I think is what that is, stated that the indefinite small changes in y were the result of indefinite small changes in x, and f of x will be a continuous function, and the numerical values of the differences, f of x plus alpha minus alpha of x, decrease indefinitely with those of alpha. So it says you can see calculus.com, larssoncalculus.com to read more of that volume. Yes? When's the first test? I'm giving it to you today. Okay, you'll have to take it in the last 15 minutes of class. No, I'm just kidding. It's a take-home test. Okay. All right, and yeah, we got about an hour left, right? A little less than that, close. Okay. So he's a potential paper topic, or others to deal with that, if you're interested in that. Or you can even go to Jacques Charles, we mentioned him in the book, to try to tie calculus in with it somehow. Cauchy is not hard. Charles will be a little harder. Okay, so here are the properties of continuity. And here's theorem 1.11. Okay? If B is any real number in the world, and remember real numbers are positive or negative, fractions, decimals, rational or irrational, okay? F and G are continuous at some value x equals C. So F is continuous at C, G is continuous at C. Then the functions listed below are also continuous at C. These are the properties of continuity, okay? Any scalar multiple of either F or G, so BF or BG, those scalar multiples are also continuous at that value C. Any sum or the difference of these two. F plus G would be continuous, F minus G would be continuous. G plus F, of course, is the same thing, or G minus F. Any sum or difference of those two continuous functions are continuous functions. The product of two continuous functions is a continuous function. F times G is automatically a continuous function. Now the quotient. Be careful with the quotients. Quotient F divided by G is a continuous function as long as that G of C is not equal to 0. Now remember, we're only looking at the point C. If G of C was 0, not going to happen. But if G of C is anything other than 0, F divided by G will also be continuous. Now, these top two here are basically your linearity definitions. Okay, you run into this in lots and lots of different courses. Okay, in math, probably concepts in other areas as well. The others happen to be true too. Okay, so this list summarizes the functions we have studied so far that are continuous at every point in their domain. And remember, every point in the domain, that definition of domain is going to be the catch here. Now, any polynomial function, remember we said this before, any polynomial has two features. We've talked about one, continuous, the other is smooth. So polynomial functions, every polynomial function, no matter how big the exponent or anything else. But remember, the exponent for every term in a polynomial function has to be positive integers, okay? Non-negative integers. You can't have a fractional form, you can't have a decimal form, you can't have a negative number as the exponent. Only positive integers. Hold on. Okay. Now, rational functions. Those are ratios of two polynomials. The caveat here, q of x can't be 0. So any value for x that would make that denominator 0, you have to exclude. Okay? Radical functions. Now remember the rules for that. F of x equals the nth root of x. That's for the domain here is any x as long as n is odd, and n again is positive integers. It can't be negative fractions or decimal. Okay? But if n is even, then x always has to be greater than or equal to 0. That's your domain issue. And all your trigonometric functions in their domains. And what's the domains of sines and cosines?
T's.
All real numbers. Tangents? Domain of tangents? Boy, it was a long time ago, wasn't it? Yeah. You want to remember? All real x's except your half pies. Cotangent? Whole pies. All real x's except the whole pies. Secant. Half pies again, just like tangent. And remember this. This is sine over cosine. Cosine is 0 at the half pies. And this is 1 over cosine. 0 at the half pies. So those are all the ones except the half pies. These two are all the ones except the whole pies. Of course, I'm hungry and talk about half pies and whole pies and make no talk about them. Okay. Combining theorem 111 with this list, you can conclude that a wide variety of elementary functions are continuous at every point on their domain, in their domains. The key is, where are the domains? Now that's the 10 o'clock test. That's not, it's pretty weather out there. They don't do the test if it's stormy. So if you hear if it's stormy, get below. Okay. But that's just the test. Wednesdays. I think they do Saturdays too, but I'm not usually there on Saturday. So, here is example 6, which is on bottom part of page 79. Now, theorem 111, as we just did, it follows that each of the functions below is continuous at every point in its domain. Wait a minute. Where was x plus sine x in that? I don't remember seeing that kind of function. Well, what is x? That is a polynomial function, right? Sine x is a trig function. Both of those are there, and this is the sum of two continuous functions is a continuous function. And where would that be true? All real numbers, because polynomials are always all real numbers, and sine and cosine are continuous at all real numbers. So the sum of those, or the difference of those, or the product of those, or the quotient of those, as long as the thing in the denominator is not 0, would be continuous. How about this one? F of x equal 3 tan x. Is that continuous? Everywhere in the domain of tan x. But what there? See, the domain of these two are all real numbers. What's the domain of tan x? Really long time ago now. Yeah, all the x's other than the half pies. The half pies are where they're discontinuous. But this, we didn't have 3 tan x in that last list, but this is a constant times a continuous function, is a continuous function. That's the kx, or kf, or whatever. Okay? F of x equal x squared plus 1 over cosine x. Is that continuous everywhere in its domain? For sure, because it's a quotient of two continuous functions, and the polynomial function numerator is continuous everywhere, the denominator is continuous everywhere, cosine is continuous everywhere. But what's the domain of this function? Is that all real numbers?
If this is cosine?
Except the places where cosine x would be 0. And where would cosine x be 0? Where cosine x equals 0? Say again? And a half pies. All the half pies. So this would be 0 in its domain. I mean, this would be continuous in its domain, but the domain has to exclude all the half pies. Positive or negative half pies. Okay, very good. All right. Wow. That was example 6. They don't do anything with it. So let's move on to the next theorem, which is a consequence of theorem 1.5, which is way back, allows you to determine the continuity of composite functions. We have already stated that once today, such as f of x is a sine of 3x. Okay, that's a composite function with the outer function being sine, the inner function being 3x. So what do you think the continuity of that would be? 3x is a polynomial function. Sine is a continuous function everywhere. Polynomial is continuous everywhere. So the composite will be continuous everywhere. All values of x. Okay? There's another composite function. The outer function being the square root function, the inner function being the polynomial function x squared plus 1. Anytime you see a square root, take a pause, okay? Because where is the inner function, x squared plus 1? Where is that continuous? All real numbers, okay? Now, where is the square root function continuous?
All positive.
All non-negative real numbers, exactly. So, you have to consider then all the values, x squared plus 1, where this is never negative. Where's that? Everywhere. Because whether x is positive or negative, when you square it, it becomes positive. Add 1 to it, even more positive. So that will be continuous everywhere. No limitation at all. Uh-oh. F of x equals tangent 1 over x. What's wrong with that picture? Outer function is a tangent function. The inner function is one over x. Okay? Where is tangent defined? What's its domain? Anything but the half-lives. Sine over cosine, cosine 0 at the half-lives. What about this one? What's this domain? Say again?
Negative infinity is 0.
Okay. X cannot equal 0. Okay. All real numbers except x equals 0. Okay. Now, so you can't have x equals 0. That's out of the question for F completely, because the innermost function never can have that. Okay? Now, if x is not 0, it's either positive or negative, right? And if you're taking the tangent of whatever those are, then the 1 over x cannot equal a half pi. Okay? So you exclude that 0 from it, okay? And then any value that 1 over x equals half pi. So in other words, x cannot equal 1 over any of your half pi's. Okay? So you also have to throw that in there. Okay. So here's theorem 112, continuity of a composite function. If g of x is continuous at c, g of x is usually the innermost function, and f of x is continuous at g of c, then the composite function given by f composed with g. By the way, you remember that notation too. That center circle is not multiplied, it's composed with it. And here's how that's defined. F of g of x. So you take the g of x first, the inner function first, and whatever its output is, you take f of that output. That's f of g of x. Then that's continuous at c. So all those I think we hit pretty well. This one says you have to exclude x equals 0 because your innermost function has to be defined there. Okay? And then the outermost function, you have to take all the values 1 over x not equal to a half pi. So then you have to x not equal to 1 over each of those half pi's. That's a rather tough one to define, but that's where it is continuous, as long as those two conditions are met. X not equal 0 and x not equal to 1 over any half pi. But fortunately, we're not going to have to do that. Let's do this. Testing for continuity. Describe the intervals interval or intervals on which each function is continuous. Where is f of x equal tan x continuous? As if we hadn't hit that enough today. What would be the intervals for that continuous? Okay, x, here's the easiest way to express it. X is not equal. The set of all x is such that x is not equal to n pi over 2. That would be the best way to say it. Okay? So that's a good description of it. Okay?
What about interval notation?
Second?
What about interval notation? Is there a way to do it like that? Or
Say that one more time.
is there a way to do it in interval notation?
In interval notation, it's going to be infinite, so that's why I did it this way. This would be, where do you want to start? Okay. Goodness, I don't know, where do we get? I'm going to do a dot, dot, dot to start with, and union with, and this will be negative, yuck, how would you say this? Let's start, negative 7 pi over 2 to negative 5 pi over 2. I just decided to start there, union that with negative 5 pi over 2 to negative 3 pi over 2. In other words, you just include all the half pi's. Union that with, and you just keep on stepping down until you get negative 1/2 pi to pi halves, negative pi halves to pi, 3 halves pi. Those would be your intervals. But there's an infinite number of them. Okay, so it goes definitely this way. That's the best I could do. I don't know. So much easier to say x can't equal 1/2 pi. Any n half pi where n is any integer. Okay? Now, G. Describe the interval on which each function is continuous. Okay? If x is not equal to 0, that's going to be sine of 1 over x. I don't know if you remember this when we talked about it. It just sort of links out here and then goes like this. And the closer you get to 0, the faster it goes up and down. Okay? But it has no value at x equals 0 because you can't take x equals 0. But if you then define that to be 0, x equals 0, I still don't think you can define it anywhere other than that, okay? And then that's on the left-hand side. On the right-hand side, it's like this, and then finally starts doing this, okay? So I can't see that there's any.
The n power 2 on 8.
What's that?
Is that n plus?
Up on the top one?
Yeah.
N pi over 2. X cannot equal n pi over 2. Where n is any integer. Okay? Positive or negative. That's what I have there. Negative 7 n pi, negative 5 n pi. Oh, you're right. Sorry about this. Where n is, okay. Is that right? No. I've got to correct that. You pointed out something that is wrong here. Those are not necessarily odds. N could be even, and that would be in whole pi then. So you say 2n plus 1 pi over 2. That way it's always odd, right? Any n you put in there, there's always going to be an odd number. Sorry about that. I don't know if you meant to catch me on that, but that's exactly, I'm glad you did. Okay, this one, I'd say it's still any x not equal to 0. Because it still can't be continuous at 0 because they'll have to convince me that x equals 0 makes it, continuous. Now, this one, though, we can do. Okay? I'm pretty sure we did this one, didn't we? I'm teaching 4 different math classes, and I know we did it in one class. Was it this one? I think it was, when we were doing the trig functions. This has a limit, and that limit is 0. If you define it here, then this can define everything. So this would be all real numbers. This would be all real numbers except 0, because that doesn't help your picture there. That would be all real numbers except your half pies, your odd half pies. So let's see what they got. Okay, here's the other way they did it. Pi over 2 plus n pi. That's another way to do it. Or you could say that's 2n plus 1 pi over 2. That comes out being the same thing. All other points are continuous except those values. So I like to say set of all x's such x is not equal to that. Okay? And this is the way you were saying, right, as intervals, and they're some of the intervals. They didn't start as low or high as I did, but those are your intervals. All the intervals that are your excluding your half pies. Okay? All right? And then because y is equal to f of 1 over x is continuous except x equals 0, sine function is continuous for all real values of x, follows that sine y is equal to sine 1 over x is continuous at all real values except x equals 0. Even though you define it there, it's still not continuous there. So we were right on that one. Okay? And this is what it looks like. Like I said, it messes around here, and then the closer you get, the faster it goes up and down. Even though you define it to be zeros there, still isn't going to tell you what happens because you never reach 0. Okay? So that doesn't help you anywhere. And then out here, so anything less than 0 or greater than 0, yeah, you can define it. Okay? All right. And then the C one, the function is similar to the function in part B, except that it oscillates or damped by the factor x. And what happens there is, as you get closer and closer to 0, this is going to 0, where this is staying between plus or minus 1, but as it gets closer and closer to 0, it is approaching 0 from the left, approaching 0 from the right, and then if you define it to be 0, 0, you got it now. Okay, because this thing can't be defined at x equals 0. Okay, but because the limit from both sides is 0, calls for that. What I call the envelope function, bringing it down, is approaching 0. Got that reward. So my rationale from before was probably wrong, but the answer was still continuous over the entire line. Okay. Now, we just did example 7, right? Yeah. Okay, we're now heading the intermediate value theorem. This kind of follows from what we did before. Here is the intermediate value theorem. It's an important theorem concerning behavior of functions that are continuous on closed intervals. Intermediate value theorem. If f is continuous on the closed interval from a to b, that means your count is continuous at a, at b, and everywhere in between. And, now here's another thing. F of a is not equal to f of b. So if your f of a is here, your f of b can't be there too. It either has to be here or here. Just not equal to f of b, f of a. And k is any number between f of a and f of b. Okay, so picture this. I guess I should write it here. People at home can't see what I'm trying to picture. Okay? Let's say this is A and this is B. Now, A could be negative or whatever. It doesn't matter. You have a function up here. Okay? Here is f of A, and here is f of B. Okay? They just can't be equal to each other. Okay? Now, K is any number between f of A and f of B. So K can be anywhere in here. It can be close to f of A, it can be close to f of B. It's just anywhere between f of A and f of B. Now what this tells you, the intermediate value theorem, if K is a number in between f of A and f of B. Now remember, f is continuous on A to B, including at A to B. So that's why I drew it past that. These are dots here, not open circles here. Okay? Dots there. Okay? On the value. Now, if K is something in there, then there is going to be at least one number C on A to B. So C is somewhere down here between A and B. Okay? Not A or B, but between A and B, such that f of C is equal to K. Now, why is that true? Because if f of A is less than f of B, or even greater than f of B, if you wrote it the other way, okay? And K is in between there, and remember, this is a continuous function between those two, then guess what? If you have a value here, in between f of A and f of B, then it must correspond to at least one value between A and B, because this is a continuous function. You can't pick up and skip anything. If you could, yeah, your K could be where you skipped and it wouldn't have a value. But it can't, because this is a continuous function. Okay? So there is some value. Let's see if I can approximate this. Let's just go across here. Well, there's a value, and there's a value. For that value K, then there's three possible values C down here. They could be, but there's going to be at least one. In this case, there happens to be more than one, but there's at least one number C in that interval A to B, such that f of C is equal to K. Okay? Why did I do it down there? Should have done it here, here, and here. Sorry, on the x-axis. Okay? So the intermediate value theorem tells you that there's at least one number C exists, but it does not provide a method for finding that C. Okay? Such theorems are called existence theorem. A proof of that theorem is based on a property of real numbers called completeness. The intermediate, the intermediate value theorem states for a continuous function f, if x takes on all the values between A and B, then f of x must take on all the values between f of A and f of B. Now, I wanted to point something else out to you. The way I drew this, there may be a few values in here that are not between. That's okay. It didn't say that. But so every value here, there's going to be at least one value in between A and B that will have, that f of C is going to be equal to K. There may be some K's down here too, or up here too, but that doesn't matter. We're not dealing with that. Okay. Now, an example of the application of the intermediate value theorem, consider a person's height. Okay? A girl is 5 feet tall on her 13th birthday. And she's 5 feet 2 inches tall on her 14th birthday. Now, do you think her height is a function, a continuous function of her age? Yes. No way that she suddenly skipped an inch or two. You know, it doesn't happen. It's continuous. There's no gaps, right? So then there had to be at least one day, and probably only one day, when she was 5'1". Then for any height h in between 5'2" and 5 feet 5'2", I just picked 5'1", there must have been some time t in between her 13th and 14th birthday when her height was exactly h, that height, 5'1" or whatever it happened to be. This seems reasonable because human growth is continuous and a person's height does not abruptly change from one value to another. Now, you let people get older, generally, here's what height is. Usually the height is some increasing function. It may not be a smooth increase, but it's going to be increasing until they get to a certain age, and then generally it doesn't change until they get older, and then it can start decreasing a little bit. You want to know why?
Tissue shrinks.
Second?
Tissue between
The
your
disc in
joints.
your vertebrae actually get compressed with age. There's also some stooping that might go on, but it also
Like also the heart, the
What's
tissue,
that?
like the disc and tissues between each of your joints.
Right.
shrink a little bit too.
Right. And yeah, it's not just in your
Yeah.
spine, though that's the major one, but any of your joints can start losing some of the cushioning between them. So yeah, you do, if you live long enough, you tend to shrink a little bit. Okay. It didn't say it was strictly increasing. Okay. The intermediate value theorem guarantees the existence of at least one number c on the closed interval. There may, of course, as I already pointed out, be more than one value c that would give you that same k. That's fine. It just says there exists at least one. And that's certainly the case. Here they showed it being a generally decreasing function, not decreasing everywhere. Alpha beta is actually greater than alpha b. Just can't be equal to alpha b. It would be greater than or equal or less than, but not equal to. Then for some value in between alpha beta and alpha b, say that value k there, this function has value c1 here, c2 there, c3 here before it reaches down. Okay? So you can't have more than one, but you always have to have at least one. A function that is not continuous does not necessarily exhibit the intermediate value property. Because if that has what we call a jump discontinuity, then guess what, folks? Or actually any kind of continuity, there could be a k somewhere in there that has no c value. See, alpha of any value here is going to be greater than k. Alpha of any value here is going to be less than k. You may have a k value and more than one k value, which is not. Now, if this was a removable discontinuity, you still have that one. If the k happens to be right through that hole, then it doesn't have a c value. For example, the graph jumps over the horizontal line of y is equal to k, and several above and below y is equal to k. Function, there is no intermediate value in between. Okay, goodness gracious. Last night was election night in Alabama. We had helped in a campaign, and there was a big gathering. This happened to be one of the few campaigns that looked like our guy was winning till right at the very end. He had 49-point-something%, but not 50%. So now he's going to be in a runoff. So we were waiting till they declared him a clear winner, and for much of the night he had been over 50%, and then right at the end he dropped to 49-something. So we stayed up very, very late, and still was inconclusive until this morning. So we stayed up all that late. So I'm kind of flaky today. So intermediate value theorem often can be used to locate the zeros of functions that locate the zeros of a function that is continuous on a closed interval. And guess what? We've been looking for zeros of functions, right? Those rational functions, where the denominator q of x, we need to know where those zeros are, so we have to exclude those values from our domain of your rational function. Specifically, if f is continuous on a to b, and f of a and f of b differ in sign, one is positive, one is negative, it doesn't matter which, then there will be values where the f of c is equal to 0. That's where we need to find those. Okay? There will be at least one 0 in between a and b. Okay? If it's a continuous function. So here's example 8. Last example in the section. Use the intermediate value theorem to show that the polynomial function f of x equal x cubed plus 2x minus 1 has a 0 on the interval 0 to 1. Okay, I'm not going to write that down again. I'll leave it alone. Okay. All right. So we need to do that. All right. Any ways to show? You want to try factoring? Good luck. I don't know how to factor that one. Okay. You could use the rational zeros theorem. Y'all may have studied that in pre-calculus algebra. I have a feeling that's not going to give us very good results either. Okay. One thing that would work, I don't know if you remember Descartes' rule of signs, that tells you there's at least one positive root 0 for this function, because you count how many changes of signs. Plus the plus is not a chain, plus the minus is a chain. So there is at least one positive real 0, but it doesn't say it's between 0 and 1. So there's not much we can do yet. But they say use the intermediate value theorem. How is that going to help us? Show that it has a 0 between 0 and 1. That's what we do. Plug in one endpoint, plug in the other endpoint. See what the F's are there. So what do you get when you say F of 0? I'll give you 45 minutes to find that answer. Say again? -1. Very good. You beat it big time. How about F of 1? And that's pretty easy too. You just add your coefficients, right? Because that's 1, that's 1. It's what? What? You said what, 2? Yes, 2. Does that show you that you have a 0 between 0 and 1? Yes, it does, because f of a is less than 0, f of b is greater than 0, and it's a continuous function. That's a polynomial function. Smooth and continuous everywhere, including between 0 and 1. So there has to be at least one 0 in between 0 and 1. That's all you have to show, that it is. Thank goodness they don't say, where is it? Okay. What you would have to do then, or I'd suggest, to get your graphing calculator and let it find it for you. And that even then is going to be an approximation. All right. Let me show you specifically how they did it. We did it the cheap and easy way. Let me show you how they did. What's that?
They did the same thing.
I can't hear you.
They did the same thing.
Yeah, they really did. But, oh yeah, they did at the top. But then they included a graph. So they did a little bit more. No, the f is continuous on the closed interval. It's continuous because it's a polynomial function. So it's continuous everywhere, specifically on the closed interval 0 to 1. Then evaluate it at 0, evaluate it at 1. That gave you -1 and 2. It follows that f of 0 is negative, f of 1 is positive. So there has to be a 0, and here's where they show it. Here's f of 0 is -1, f of 1 is +2. Somewhere in between there is a c. Again, it didn't tell you what the value was, but that it exists. Okay? That's all the intermediate value theorem will tell you. To find it, you have to do some more head scratching. Okay. And here's one way to do it. Call it the bisection method. for approximating real zeros of continuous function. Similar to the method used way back in example 8, wherever that was. If you know a zero exists on the closed interval a to b, then it must lie somewhere between a and a plus b over 2, or between a plus b over 2 to b. Okay? In other words, the midpoint between, if this is a, this is b, it's either going to be between a and halfway between that, or between halfway between it and b. That's the midpoint. Okay? From the sign of this one, so basically take the midpoint in between a and b, and then plug that into f. If that sign is the same as f of a, then it's different from f of b. If it's different from f of a, then investigate here, otherwise you investigate there. So what you do, you keep doing this, bisecting that, and you get smaller and smaller. Now, Archimedes had a name for this kind of approach. He was doing something else much more complicated than this. He was trying to find the circumference of, no, the area of the circle. And they didn't have the formulas back then. So what he did, he put a square, perfect square around the circle, also a perfect square inside the circle. Okay? So the ones on the outside touch this way, ones on the inside touch that way. Okay? And he calculated the area of the square, the big one and the small one. And he knew the area of the circle was something in between. So then he drew pentagons. Perfect pentagon, outside and inside. Even back then, this is like 200 or 300 BC, okay, before Christ, he was able to do the calculation. Tedious they are, very tedious, breaking one in the triangle and doing the areas of the triangle. Inside, outside is something in between. And then he did perfect hexagons, and perfect septagons, and perfect octagons, you know, inside and outside. And he's getting closer and closer to the perfect circle there. Okay? And when he got it so it was within so many digits of precision, he said, let's stop. And he called that method the method of exhaustion. Okay? Because he just got tired of taking more and more notice. The more sides you got, the more little triangles you got. And then inside, outside, I would get exhausted really quickly. And you can get exhausted pretty fast doing this too, but just take the midpoint. When you have one above, one below, take the midpoint between the two, whichever that is. And then the midpoint here, and then the midpoint there, and the midpoint there. And after a while, you're really, really close. And when you get tired of doing it, method of exhaustion, you quit. Say, that's approximately the answer. Okay? Now, that's not how your calculator does it. Okay? But that's one way to do this. And that is the end of 1.4. Okay. And at the end of your thing is called technology. You can use the root or zero feature of graphing utility. That's what I said you should use. So in 1.4, homework exercises include any of the odds 5 through 9. All those odds are at calcchat.com, 5's at calcview. Any of the odds 11 through 29. They're all at CalcChat, 11's at CalcView. Any of the, either 31 or 33, they're both at CalcChat, 31's at CalcView. Either 35 or 37 or both, they're both at CalcChat, 35's at CalcView. Any of the odds 39 to 57, they're all at CalcChat, 47's at CalcView. Any of the odds are, 59 through 63, they're all at CalcChat, 61's at CalcView. Any of the odds 65 to 69, they're all at CalcChat, 67's at CalcView. Either 71 or 73 or both, they're both at CalcChat, neither one of them are at CalcView. Same thing for any of the odds 75 to 81, they're all at CalcChat, but none of those are at CalcView. Any either 83 or 85 or both, they're at CalcChat but not at CalcView. Do 87. It's at CalcChat, but not at CalcView. Any of the odds 89 to 93, they're both at CalcChat. All are at CalcChat, but none of them at CalcView. Then do any of the odds 95 to 99, they're all at CalcChat, 95's at CalcView. And then you can, if you're into exploring, you can look at 101 or 103. I don't know if those are at CalcChat or not, but you can look them up and see. Or you can forget those if you want to. There's a couple true false, actually a few more than that, 105 to 109. Imagine those at CalcChat also. And they're good things to think through. I wouldn't spend a lot of time at it, but at least try to think through it. And you can also think about 111. 113, if you want to dig into that, you can. Let's go back. Do any of the odds 113 through 127. Now, some of those get a little esoteric, so don't get too bogged down with them if you don't want to. Those are a little bit beyond what I'm going to test you over. Okay? And you see Dirichlet's function we mentioned before. There's also a signum function that we didn't mention, and this would be one that you, if you want to write about either one of those two, you can. Or okay. All right, now, whoa, we just went out of time, didn't we? Isn't it? Yeah.